Hello and welcome back to the SSL lecture series. This is episode 8 and I am Saravanan learning along with you. So today again we have a very packed session, so we will quickly go through it. The agenda is whenever you encrypt, for example in the past episode I showed a demo of how to do encryption using DES etc. right. So instead of looking at every time using the octal dump in hexadecimal character, the alternate way people commonly use is to observe the binary output as a readable text. So we will see how to do that. We will also see what is Base64 encoding and where it is used. In particular, how Base64 encoding is used in Ssl Certificate in the PEM format. We also see a demo using openssl, and then we learn instead of every time providing key and initialization vector, how to use a password. So in that case, how a password is getting converted into corresponding key and IV. So typically something called password based key derivation function is used. We will also see a demo of it using Python. Then we will see how to use password instead of key and IV using DES. Here again, even though you might think that DES no one is using nowadays, so the idea is not to explain DES, the idea is to introduce the concept of using password instead of key IV. You can use any block cipher. Just for simplicity, I am using the DES here, okay? Then whenever you observe openssl, right, whenever you provide password, openssl automatically adds something called a salt value. So we will see what is a salt and how it is used along with the password. Then we move on to triple DES. We will tell the difference between what is 168 bit and 192 bit when using triple DES. We show a demo using the keyring option 2. Remember in the past lecture I told keyring option 2, 1 and 2, right? 1, 2, 3. So we will go through how to do 3-dash encryption using keyring option 1 and keyring option 2, and finally we will see a quick demo of AES using Cbc mode with different key sizes. Okay, let's get started. Okay, let's first start with a demo again using the DES. We see how to view the binary output, encrypted binary output into a readable text form. Okay, as usual I will take the echo command. The word I am going to encrypt is secret. Okay, so I will call openssl enc module -des. Then I am going to say encrypt this, so I will use -e. Okay, then I have to provide a key and IV, right? So I will give a IV. For simplicity I will use all the same character 1 2 3 4 5 6 7 8. Okay, key also I am going to use the same one. Okay, I am going to use the same key here. So let's first look at how does it look like, how does the binary look like. So this is the binary. Usually we will do a octal dump, right? Here instead of doing the octal dump, I am going to use minus lowercase a. This means use Base64 encoding. Later I will tell you what is Base64 encoding. Look at the output. Now instead of watching in binary, you are able to read the characters, right? So this is what we mean by Base64 encoding. Okay, so let's take another example. This time I am not going to use DES. Instead straight away I want to use the Base64 encoding. Okay, so let's start with the fresh screen, and if you just say -a, that means use Base64 encoding. So let's see how the output look like. So this is the Base64 encoding of the word secret. Okay, now I will use a very simple 3-letter word. I will just say A, B, C, only 3 letters. Okay, let's see what is the output we are getting. So this is the output we are getting, right? Let's note down this output. Y, W, J and then the lowest k. This is for ABC, right? We got for ABC. Now let us see what is Base64 encoding. So before we jump into Base64, what is Base 2? Base 2 is nothing but 0 and 1. There are only 2 states, right? 0, 1. There are only 2 states in Base64. Okay, 2 states. So what is Base 10? The decimal number system that we are all using, 0, 1 up to 9, right? So there are total 10 states are there. That's why we call it Base 10 encoding. So what is Base 16 encoding? Base 16 is nothing but your hexadecimal, right? After 9 you will have ABCD up to F, right? So together you have 16 states. That's why it's called base 16 encoding. Similarly, base 64 encoding is nothing but you start from 0 all the way to 63. So total there are 64 different states. Okay, 64 different states are there. Now one easy way to represent this state is you create a table. Let's create a table. So we start with the value 0. I am going to assign the letter uppercase A. Value 1 I will assign uppercase B. You continue like this. So 0 0 is your uppercase A. You will continue like this. You will hit uppercase Z. Then you start with lowercase a. You continue. Then you will hit lowercase z, right? So A to Z you have 26 character. Lowercase a to Z you have another 26 character. So total 52 characters, right? Now you take 0 all the way you go up to 9, right? So 0 to 9 you have another 10 characters. So 22 plus 22 52, 52 plus 10 62. I am going to add two more symbol, the plus symbol and forward slash. So that gives two more symbols. So 62 plus 2 64. So this table is called base 64 encoding table. Okay. Now let's try to do the encoding of these three characters A, B and C. So before that we want to know what is the ASCII value of A, B and C. Okay. So this is the A, this is my B, this is my C. Let's quickly look at the ASCII value of A, B and C. So if you look at my screen, I am just type the ASCII command hexadecimal, hexadecimal 61 is lowercase a, 62 is lowercase b and hexadecimal 63 is lowercase c. Okay. So let us try to do the base 64 encoding of these three characters A, B and C. We learned that this character is nothing but hexadecimal 61, hexadecimal 62 and hexadecimal 63, right? So base 64, in order to provide 64 state, how many bit you need? Let's say take a simple example with 2 bit. What are the different combination we can produce? 00, 01, 10, 11, right? So you can produce 4 combination, which is nothing but 2 power 2. Similarly, if you want to produce 64 different combination, you need a minimum of 6 bits. Okay. So 2 power 6 is nothing but 2 times 2 4, 4 times 2 8, 8 times 2 16, 16 times 2 32, 32 times 2 64. You get 64. Okay. 2 power 6 is nothing but 64. So to represent 64 different state, you need a minimum of 6 bit. Okay. When I write this right, I have 3 bytes here. So 3 times 8 bit is equal to 24 bit. So if I want to convert into 64 different state, each state to represent I need 6 bit, right? So I can rewrite this into 4 times 6 bit. Okay. 4 times 6 bit, which is nothing but again 24. So to do this encoding, I have to take 3 character at a time and convert them into 4 character in the base 64 encoding. So let's do that. If you see an example, you will remember forever. Okay. So let's start this example. So let's take the 61, 62, 63. Okay. If I will write 61 this is hexadecimal. 61 I am going to write in binary. So 6 is nothing but 0, 4, 5, 6, 0. Okay. So this is 6 in binary. 1 is nothing but 0, 0, 0, 1. 62 is nothing but 6 is nothing but 0, 1, 1, 0. 2 is nothing but 0, 0, 1, 0. Then I will write 63. 63 is nothing but 6 is nothing but 0, 1, 1, 0. 3 is nothing but 0, 0, 1, 1. Okay. Now my job is to divide this fellow into 6 bit at a time. So first 6 bit, second 6 bit, third 6 bit and fourth 6 bit. So 1, this guy is 2, this guy is 3 and last fellow 4. So I converted into 4 6 bit. Okay. I took 3 characters at a time and converted into 4 6 bit. Now what is the value of this in decimal? The value of this in decimal is nothing but 16 plus 8 24. Then this fellow is nothing but 22. This fellow is nothing but, if you convert, I am just doing mental calculation. So there is a delay. 8 plus 1 9. And this fellow is nothing but 8, 16, 32. 32 plus 3 is 35. Okay. Now what I am going to do is, I will look at the base 64 table to figure out what is the corresponding character for these decimal numbers. Okay. So let's do that. Okay, here we are looking at the base 64 table in the Wikipedia. So if you look at the digits that we found out, so we have 24 here, which is nothing but Y. 22, where is 22? 22 is here, which is nothing but W. Then 35, 9, right? 9 is nothing but J. What is the fourth thing we found? 35. 35 is lowercase j. That means the letter ABC, if you convert into base 64 encoding, this fellow will become 4 characters. That is 24, 22, 9 and 35, right? So 24 is nothing but Y, 22 is nothing but W, 9 is nothing but uppercase J, 35 is nothing but lowercase j. Okay, so we got 4 characters Y, W, J and lowercase j. So that's what the base 64 encoding command output is produced by openssl. So let's quickly see what openssl has produced. Okay, the output I am getting is Y, W, J, lowercase j, which is exactly what we derive manually, right? Okay, now what happens if you only have 2 letters? So let's see if you only have 2 letters, like what happens if you only have 2 letters. So let's see, let's work out again what will happen if you only have 2 letters. Okay, here I have only 2 characters A and B. We know that the corresponding hexadecimal value is 61 and 62, right? But in order to convert into base 64, at the minimum we need 3 characters. Remember, 3 times 8 we will convert into 4 times 6. 3 input we will convert into 4 output letters, right? That means 1 byte is missing, so I am going to add 1 byte of 00 as my padding. Okay, so I will add 00000000. Now as usual I will divide into 6, my first 6, my second 6, my third 6, the fourth 6 are all 0. So if you get 6 bit of 0, you have to use the character equal to. This equal to represents padding. Okay, equal to represents padding, that is all 6 bit are zeros. Okay, this one now. So what is the equivalent of this? This we already know, right? 24. So what is the second character now? This also we already know, right? That is nothing but 22. So the third character here is 4, 8. This represents 8. Okay. So let's look at in the ASCII table again. So 24 we already know. 24 is uppercase Y, right? Earlier we already saw. 22 we saw is uppercase W. This is in the base 64 table. From Wikipedia we refer the table, right? So 8 is nothing but, I told you 0 is A, right? If 0 is A means 8 is nothing but A, B, C, D, E, F, G, H, I. You will get uppercase I. Okay. Then last you will use the padding. So what you will get is Y, W, I and a single equal to character. So let's quickly see the output of the openssl. See, whatever we derive manually we got, right? Y, W, uppercase I and a equal to symbol. Okay, what will happen if I only have one character as input? I only have one character as input. Again, let's do the workout. Okay, now I only have one character. Okay, that means it's hexadecimal 61, which is nothing but 0110. 1 is nothing but 0001, right? That means I have to add 2 bytes of padding, 0 and 0. Okay, let's add 0000000000000000. Remember, we always convert 3 8 bits into 4 6 bits. Okay, so let's take this first 6 bit, second 6 bit, third 6 bit. If you notice the third thing and the fourth thing is nothing but all zeros, that means you replace with the equal to, equal to represent padding character. So this fellow is nothing but as usual 24. This fellow is nothing but 8, 16, right? So 16, what is 16? 16 is nothing but the character Q in the base 64 table. Okay, this we already know, character uppercase Y. So that means the result you got now is uppercase Y Q equal to. So let's verify this YQ double equal to in openssl. So we are in openssl. I am going to press enter. We should get YQ double equal to, right? Exactly we got. That means in the input, if it is a perfect multiple of 3, you don't get any padding. If you have only 2 bytes, that means you need 1 byte of padding. That's why you get an additional equal to here. When you have only 1 byte, you need 2 byte of padding, which will automatically end up with the 2 equal to in when you convert into base 64. So whenever you handle base 64, you will either see a single equal to or double equal to or no equal to. Okay, you will ask what is the purpose of base 64, right? Why we have to convert like this? I told you the purpose is to see the binary output in a readable format. Why it is needed? In the past days, in the olden days, when SMTP protocol was there, when people were sending email, right, you cannot do binary attachment like you are doing nowadays, like photos, video, audio, all those binary attachment you cannot do. Instead, what people did was, if you want to attach a photo, you use the base 64 encoder, convert your entire photo into readable text, and then cut and paste the text in your email. The receiver will take that value and then do a base 64 decoding, convert back into photo. So all the binary data was simply sent as a plain ASCII text, or whatever the base 64 table characters, A to Z, 0 to 9 plus and / character. Okay, so that's the history of the base 64 encoding. Okay, why we need to talk so much about base 64 is because later you will see when we talk about Ssl certificate, right? We will talk about something called Ssl certificate. Don't worry about this. We have a separate episode to deal with this. So a typical Ssl certificate, usually you have client server. The server will send a certificate, right? But as soon as you connect to a Ssl server, during the handshake process, it will send a certificate. Again, don't worry about the handshake process. We will do elaborate study on that later in separate episode. Just for the time being, just focus. The server, when you connect, it will send a certificate for authentication purpose. This certificate, whenever you handle in OpenSSL, right, it has to be in a format called PEM. Again, don't worry about what is this PEM format. We have a separate episode for it. The certificate in PEM format is stored in the so-called base 64 encoding format. Okay, don't worry about the PEM exact detail. Just assume that there is something called certificate. It is stored in some format called PEM. It uses a base 64 encoding. Let's see a quick demo of how the certificate will look like in base 64 encoding. Okay, again I am in OpenSSL. I am using the module called sclient and the command called connect. Then I am trying to connect to fi.com:443. So I'm going to press enter. Okay, I press enter, it got connected. It is waiting for my command. So I will just quit by pressing a Ctrl+C. Okay, now if I come back, you would have noticed that as soon as the OpenSSL got connected, the server will do a handshake process and then it will start sending the certificate, right? The entire certificate starting from begin certificate all the way here. If you come down, right, end certificate, this fellow is in base 64 encoding. Look at this guy. There is a single equal to here, right? That means it is not in multiples of 3. The input was not in multiples of 3. It needed 1 byte of padding, which ended up with a single equal to at the end. Okay, if you notice all these characters, you will only see A to Z, lowercase a to Z, plus symbol and / symbol, which is nothing but your base 64 table. Okay, this equal to character is used for padding purpose. So far what we have learned, there is something called base 64 encoding, which uses a plain ASCII A to Z 0 to 9 plus /. Okay, this is used to represent binary in readable plain text format. Okay, that's all we learned so far. Next, what we are going to see is, so far, let's say when you want to encrypt, right? So far what I was doing, I usually call OpenSSL ENC module. I will say let's say DES encrypt. I will usually give a IV and then I will give you a key, right? Now what I am going to do is, instead of manually giving this key and IV, I will simply use a password. If you use a lowercase k, you can directly provide a password. For example, I will use the password Apple. Okay, there is an option in OpenSSL called uppercase P. Uppercase P means do not do encryption. Instead, whatever key IV value you are using, can you show me that value on the console? Don't do the encryption. That is the meaning of -P. So I am going to invoke that option. OpenSSL says it automatically generated a key for us. It automatically generated a IV for us. You might be wondering, right? I only gave the password. How the fellow know the key and IV, right? We will see how it is deriving a key and IV from the password. For this, there is a special algorithm called password-based key derivation function. So the algorithm name is password-based key derivation function. Okay, this is a standardized algorithm. You can find this algorithm in the RFC. However, in OpenSSL implementation, they use something very similar to this, but it is not a standard. It's a proprietary for OpenSSL guys. It is almost similar to this. The idea is exactly same. Okay. So what it does is this function will take the password as input. Whatever password you are giving, it will take it as an input and then generate random output. You can specify how many number of bits you want. For example, when you use DES, you can specify I need 128 bit output so that I can take 64 bit key from it and another 64 bit value as IV. Okay. So given a password as input, it will produce a random number as output. You can specify the length of random number that you need. There is an advanced version of this function called password-based key derivation function version 2. So all this thing was originally came as a standard called public key cryptography standard. Remember, we have already talked about this. I told you this was invented by the RSA security company, which itself was formed by the founders of RSA algorithm, public key RFC algorithm. Okay. So they published lot of standard. One of the standard is called PKCS version 5. This standard covers the so-called password-based key derivation function. Later, it was also documented in the RFC. So the latest version of, there are multiple versions of this RFC. The latest version of the RFC is RFC 8018. So I can quickly show you where it appears in the RFC. Okay. So we are inside RFC 8018. So we are in RFC 8018 here. It's called password-based cryptography specification version 2.1. So if you look for password-based key derivation function, here you will see version 1 and version 2, right? So let's jump into version 2. So this is what the version 2 is saying. Don't worry about it. So I will just briefly tell you what it does. Okay. So typically this so-called password-based key derivation function, right? This fellow typically takes a password. Usually you will provide some kind of hashing algorithm. You will say what hashing algorithm you want to use. Then you will provide a password value. You will also provide a salt value which you want to use with your password, and then you typically tell what is the number of iterations you want to use for the hashing algorithm. Okay, number of iteration is a count, is an integer value, okay. Then the number of output bit you want. Okay, I will use the DES as example here. In DES I need a total of 128 bits, 64 bit for key, 64 bit for IV, right? So 128 is a small number, so I will just say I need 256. There is a hashing algorithm called ssl 256, right? Let's say I want to use ssl 256. It will produce a 256 bit output. I will only take the first 128 bit and throw away the remaining. Okay. So my hashing algorithm, I will say I want sharp 256, but not the ordinary hashing algorithm. There is a special version of hashing called HMAC ssl 256. Don't worry about HMAC right now. In the next episode, we are going to elaborately see what is the MAC, what is the HMAC, all those things we will see elaborately. Okay. For the time being, you assume that HMAC 256 is a cryptographically safe hashing algorithm. Okay. It produces a random number as output. You don't worry about what exactly is HMAC. We have a separate episode for it. Okay. Then you provide your password. You provide your salt value. You don't do the hashing just one time. You tell a count. For example, I can say I want to perform 4096 iterations. Repeatedly it will do the hashing for a very long time, up to this number of times. Okay, number of time you want to hash that value. The idea is when you generate a key from the password, you have to do the operation in a very slow format. Purposely it was designed that way. You have to do it in a very slow format, so that if an attacker try to attack, right, to every time he guess a password and try to generate the so-called key, it will be very, very slow. It was purposely designed this way. Okay. Then finally you tell how much of output you want. For example, in this case, I only want 128 bit output. Okay. So this is just an example I am telling. So I told you OpenSSL actually doesn't use this thing. Instead they have a similar algorithm, but the proprietary algorithm. Okay. There is another places you quite often use this so-called password-based key derivation function too. That is in your Wi-Fi, right? If you use home Wi-Fi at home, most of us currently uses the so-called Wi-Fi protected access version 2, right? If you have a home Wi-Fi router, definitely you will be using WPA2. If you are using any of the previous version, please change it immediately. The previous version are not safe. You must use WPA2. WPA2 came as a part of the wireless standard 802.11i. This fellow uses a protocol called CCMP, which is nothing but counter mode CBC MAC protocol. Counter mode CBC MAC protocol, which is again nothing but it is using AES in CCM format. Okay, CCM mode of operation. CCM stands for counter mode CBC MAC protocol. All these things we have already discussed in the past episode, right? Did we saw? Now I myself forgot in which episode what I told. Okay, so okay, there is some mode called CCM mode. It's called counter mode CBC MAC protocol. So in this protocol, in the so-called WPA and WPA2 protocol, in the home, are you configuring a key and IV? No, right? You are simply using a password for your Wi-Fi, right? So when you provide a password, automatically this password will get converted using the so-called password-based key derivation function 2, and then it will convert into whatever necessary keys. For example, in Wi-Fi, we typically use a 256-bit so-called pre-shared key, okay? So we don't go into the Wi-Fi protocol now. I'm just giving you an example where you are converting your password into key using the so-called password-based key derivation function. OpenSSL using a similar algorithm to convert your password into key and necessary IV values. Okay. So we will see a quick demo of how to generate this so-called key whatever value using the PBKDF function. Okay, I'm going to use the Python for this. You can use whatever language you want. Just for simple demo, I usually use Python because in Python it's always very easy to show a lot of things in a quick way. So I use Python 3. It comes with a library called hash library. So I'm going to use this hash library. So let me call this hash library. Okay. Inside the hash library, it has a password based key derivation function using a HMAC. Again, don't worry about HMAC. We have a separate episode for it. We will see about this. So I am saying I want to use SHA-256 HMAC in the not ordinary SHA. Use SHA-256 in the HMAC mode. What that means, you don't worry. We will see in the next episode. Then I am going to provide my password. For simplicity, I will use the word password. Then I am going to provide a sol. The prefix B represent I am using a octet string. Otherwise, Python will take every string as Unicode string. Okay. Unicode string is not a single byte string, it's a double byte string, so it will create unnecessary confusion. So when we use the prefix B, it means I am providing a octet string, not a Unicode string. So I have to provide some salt, so I will just use the word salt itself as a salt. Then I am telling, okay, you perform the hashing for 4096 times. For example, in Wi-Fi protocol, we actually perform 4096 times round of hashing before we generate our 256-bit value. So this fellow will create an object and the object will get stored in the variable called h. Now I need to see the object in hexadecimal format, right? So to simplify things, I am going to use another library function called binASCII. So I will just say binASCII. It comes with a function called hexlify, which means whatever I am throwing at you, convert into hexadecimal format and show the output to me. Okay. I am going to see the output in hexadecimal, so this is the one. So here I have produced 256 bits of output. Okay. So this is, if you don't believe me, we can see the length of this. Okay. So the length of this is nothing but 64, right? 64 times 4, which is 256 bit. Okay. It is showing in bytes. Because it's a hexadecimal character, we have to multiply by 4. So the output is a 256 bit. So we can take the first 128 bit from it, remaining you can throw away. So you can divide them into two, key 64 bit, IV 64 bit. That's how OpenSSL is generating the key IV from your password. I told you OpenSSL doesn't use the PBKDF2. It uses a different version of it, but the core idea is still same. Okay. Now what I am going to do is, again I am going to ask the OpenSSL using a password. Hereafter I am not going to use key and IV. I will directly use a password. So I am going to tell OpenSSL, don't do the encryption. Can you show me what is the key and IV that you have generated? For that I already told you we can use the minus uppercase P, right? So this fellow is showing this is the key it has generated. How it generated? It uses the password based key derivation function to generate. It has its own version of this algorithm. It's not using the RFC one. So IV, it is showing the corresponding IV that it has generated. But if you notice, it also used something called salt, right? So what is a salt? So let's quickly see what is a salt. The salt is also the same size, right? The salt is also equivalent to the block size, right? So what is exactly a salt? So to understand this, what I am going to do is, let me call the same command again. The password is still same, right? So you should get the same key and IV, right? Let's see what happened. See, even though I did not change the password, the key is changed, the IV is changed, right? The salt also changed. So I am going to call this function again. Again, I have not changed the password, but look at the output. Every single time salt is changing, key is changing, IV is changing, although I have not changed my password, right? That is the very purpose of the value of salt. When you use a salt along with your password, it will always produce a unique key and IV. It will never reuse the key and IV, okay? It will produce a unique key and IV when you use a salt, okay? So we won't go into the too much details of what is the security of the salt and all those things. I will give you another simple example. If you use operating system, right? All the operating system does this. I will just take a Windows as example. Whenever you create a user ID on Windows, right? You always assign a password to the fellow, right? So internally, Windows will not store your password. As soon as you type your password, it will take the hash value of password. When it takes the hash, it will automatically, it will take the password, append your password with a salt, and then the resulting value, it will store the hash value, and the whatever the salt value it use, it store these two value in the database, okay? It will never ever store the plain text password directly in the database. It will always generate a hash along with a, it will take a password along with the salt, it will calculate the hash. It will also store the whatever salt value it use, it will store. Let's say later some user comes and login, right? Windows login. As soon as you type the password, internally the OS again perform the same algorithm. It will take the password the user type, it will append the salt, it will, because it will know based on the user ID, it will check the database for this user ID, this is the salt I am using. So it will retrieve the salt, then take password and salt, and then it will create a hash value, and then compare whether this hash value is same as this hash value, okay? So if you introduce a salt, you don't have to store the, if you introduce a hash and salt, you don't have to store the corresponding plain text in the database. So in the past, people were stealing all the plain text password. So with this mechanism, it adds some additional security, and every time when you change the salt, the resulting hash value will be different. So in a way, the salt is acting like a nonce value. You remember when we do the encryption, remember I told you, right? Whenever you give x1, you get y1 for the same key k. But if you introduce a random number, every time you change the random number, your output will be different, even though your input is same, right? When we discuss about mode of operation, when we discuss probabilistic encryption, I gave this example, right? So R is acting as a nonce, so the salt is in a way acting as a nonce value, number used only once, okay? So we don't go too detail into the salt, just assume that if you use the salt along with your password, you can generate a different key and IV values, okay? It provides more security. Okay, next we are going to see a quick demo of the 3DES encryption. In particular, I am going to show you the 3DES in CBC mode of operation. So if you remember 3DES, we talk about the keyring option 1, right? So what is keyring option 1? If you remember, K1 is not equal to K2 is not equal to K3, right? In DES, the key size is 56 bit, right? So if you take 3 keys, the total key size is 168 bit. But I already told you, even though key size is 56 bit, in practice, including the parity bit, you have to use 64 bit, right? That means the effective key that you are using is 60 times 3, 180 plus 290, 192, 192 bit, okay? Internally, it will throw away every 8th bit. Every 8th bit is a parity bit. Internally, it will throw away all the parity bit, and it will effectively use only 168 bit, okay? So if somebody asks what is the key size of triple DES in keyring option 1, you should say 168 bit, not 192, okay? Okay. So we will also see another demo of keyring option 2. keyring option 2, if you remember, K1 is not equal to K2, whereas K3 is nothing but K1, right? Your K3 is nothing but K1. That means I only need 2 keys. So 2 key means 56 into 2. How much you need? 112. But in reality, you cannot use 56. So you need 64 bit. So 64 into 2, you need 128 bit. Okay. Even though you provide 128 bit, DES algorithm internally it will throw away all the parity bit. Effectively, it will take only 112 bit. This you should remember. So first we will see a demo of this, and then we will see a demo of this. The key is you are taking 3 key, but the IV is fixed. IV is always equal to the block size. What is the block size in triple DES? The block size is still 64 bits. Okay. Here also the key you are taking 2 key, but the IV is fixed. IV is always equal to your block size, which is nothing but 64 bit. Okay. So let's see a quick demo of triple DES using CBC mode of operation. Again, I am going to encrypt the word secret. OpenSSL ENC. So before I call the 3DS, I want to quickly show you the alias that OpenSSL use. Okay. So this is the OpenSSL ENC man page. If you look at the man page, here you will see that DES3 is nothing but, this is the DES3, it is nothing but alias for DES EDE3 CBC. Why it says EDE3? If you remember, how do we encrypt in triple DES? Do you remember? If you watch my one of the past episode, in 3DES, when you use the keyring option 1, right, you take the first key, this is your plain text, you take the first key, encrypt using plain text, encrypt using key K1, whatever output you take, you decrypt using key K2, whatever output you encrypt again using key K3. This is how the triple DES is working, right? That's why the word EDE, encrypt, decrypt, encrypt, that's what EDE. EDE3 represent we are using triple DES. Okay. If you the OpenSSL use a notation. In OpenSSL, EDE3 means you are using keyring option 1. That means all the key are different. In OpenSSL, if you just say EDE, it means keyring option 2. That is, you are only using 2 unique keys. Okay. So that is the notation used by OpenSSL. So if I say DES3, which is nothing but an alias for DES EDE3 CBC in keyring option 1. For keyring option 2, you basically use DES EDE CBC. Okay. So this means 2 key triple DES. You are using keyring option 2 in CBC mode. Okay. So let's see the demo. So minus E, I am going to say triple DES 3. Then I will use the password. Hereafter I am not going to use the key. I directly use the password. Let the OpenSSL derive the key and IV. Okay. So I don't want to encrypt first. I want to see what is the key and IV value it is generating. So look at this. It is automatically generated a long key, right? So let's see what is the length of this key. Python 3. What is the length of this key? So the length of this key is nothing but, okay, length of the key is nothing but 192 bits, right? Because 64 times 3, 192. Okay. Internally it will throw away every 8th bit, which is a parity bit. But if you look at the IV is only 64 bit. IV is always equivalent to the block size. Okay. IV don't change, only the key size will change. Here we are using keyring option 1 and we are going to encrypt now. Okay. So I'm going to encrypt. I'm going to see my encrypted output in Base64 encoding. So this is my encrypted output in Base64 encoding. Okay. So let's do the decryption of it. I have already encrypted. If I do the decryption, you have to use lowercase d. The algorithm is still same, DES3. Password is still same. Okay. So I am going to do the encryption. Oh, sorry, decryption. So I successfully got back my secret. Okay. So we did a encryption and decryption using triple DES using keyring option 1. Okay. Now let's do the same thing, but instead of triple DES, I will use a EDE-CBC. That means I am going to use triple DES with 2 keys, keyring option 2. This is the notation used by OpenSSL. Okay. So I will first do the encryption and I will see the result into Base64 encoding. That's why I am using -A. So this is the encrypted output. and I can decode now. Okay, openssl enc minus d for decode. The cipher that I am going to use EDE-CBC means use keyring option 2 in triple DES. Okay, minus k, password is still same, so I got back my original plain text. So far what we saw, triple DES encryption and decryption using keyring option 1, triple DES encryption and decryption using keyring option 2. Okay, now let's see one more example. Okay, now what I'm going to do is I'm going to pass the option. By default, if you don't say anything, openssl automatically will add a salt, right? So I want to show you without salt how does it look like. Okay, so I'm going to tell openssl as usual don't encrypt. Let's first see with the salt how does it appear. With the salt, it is producing some key and IV, right? It is using this particular salt value. Salt value is also equivalent to the block size. So without salt, you have to specify no salt. If you say no salt, if you say no salt, it will not use the salt. So it has generated the key and IV. So now I again invoke this function. Look at this. Again the key is same, IV is same, right? So if you do not use the salt, whenever you use the password, always you will end up with the same key and same IV. So I will again do one more time. You always end up with the same key and same IV if you don't use the salt. So you must use the salt. Whenever you handle password, a password without a salt is not worth. Okay, security wise it's very weak. Whenever you handle password, you must always use the salt along with your password. You can even manually pass the salt if you don't want the openssl to auto generate. For that you need to use the uppercase yes. Okay, for example I am going to cut and paste the salt here. I will cut and paste here. Okay, this is the salt I want to use. Minus uppercase P. See, I got the value, right? So we learn how to use the salt, how to generate output without the salt using the minus no salt option in openssl. Okay, before we end this episode, we will quickly see one more demo for AES. I am going to use the AES in CBC mode of operation. In AES, you all know the key size. There are 3 different key size that AES support: 128, 192 and 256 bits, right? However, in AES, the block size is always fixed. The block size will never change. Only the key size will change. That you must remember, okay? Also, AES will support lot of mode of operation. I told you we should never ever use the ECB mode. So one of the popular mode of operation in AES is cipher block chaining mode. You also have Galois counter mode. You also have counter mode with CBC MAC. So these are the most popular. In the recent days, this become very popular. GCM becomes very popular. Okay. So the demo we are going to see is using the CBC mode of operation. As usual, before we see the demo, we will quickly look at the man page of openssl to see what aliases are available. So this is the man page of openssl ENC. If you go up right, you will see the, where is the AES? Here is the AES. So when I say simply AES 128, it actually represents the alias for CBC mode of operation. Quite often in SSL TLS, right, if you don't specify the mode of operation when using SSL TLS, internally it will usually assume CBC, okay? But if you are in doubt, it's better to check exactly what mode of operation it is using. But most of the time you will find when people use CBC in SSL TLS, not other places, okay? In SSL TLS, when you don't specify mode of operation, by default they assume you are going to use CBC, okay? So openssl also use this notation for AES. So in AES, if you just specify AES, it automatically uses the CBC mode of operation. Okay. As usual, I am going to encrypt the word secret using the AES 128 minus lowercase e for encryption minus lowercase k means I am using a password. First, I don't want to encrypt. I want to see what kind of key and IV it is generating. So I am using minus uppercase P. So if you notice that as usual the fellow uses a salt value and then it generated a 128 bit key. The IV is always equivalent to block size. In AES the block size is 128, that's why it uses a 128 IV size. Okay. Now what I am going to do is instead of 128 I will say 192. So the IV size is still the same, right? Still it's 128 bit, whereas your key size is now increased to 192 bit. Okay. IV size will never change, only the key size will change for AES. One last example I am going to show you in AES 256. Again the key size has increased to 256, the IV is still same, the block size 128 bits, okay. So let's see a quick demo of how to do the encryption. So encrypted value of the word secret using AES 256 is this, and then we can do the decryption. For decryption is exactly same, openssl enc, only difference is you have to use -d, okay. All the remaining are still same. AES 256 password this. So it successfully decrypted, we got the plain text back, okay. I think with this we have to stop here. So we have come to the end of the episode 8. So let's do a quick review of what we learned today. So in the beginning I showed whenever you do the encryption, so far we have see the output of binary output using the octal dump, right. So instead I told you we can also use the Base64 encoding to convert your binary output into readable text. Basically Base64 uses A to Z, A to lowercase z, 0 to 9, and then the character plus this, and this is used for padding, okay. Either you will see single equal to or double equal to for padding. What it does, it usually converts into 3 8-bit value into 4 6-bit value, okay. That's how the Base64 encoding works. I told you Base64 was created in the olden days. When people were sending email, there was no option to do the attachment, so they convert your binary files like photo, audio into plain text, cut and paste the plain text in your email. On the receiving side they will decode and convert back. Luckily this Base64 is also used in Ssl certificate with openssl. In particular Ssl certificate has lot of format. One of the most famous format is called PEM. Don't worry about all the detail, we have a separate episode to deal with all these things. Just understand that Ssl certificate PEM format use Base64 encoding, that's all. This one line is enough for you to remember. Then I also told you every time there is no need to provide key and IV, you can also use a password. In that case it will use something called password based key derivation function, which is documented in RFC as well as in the PKCS standard, right. Then we saw a demo using DES and a password, and we also saw how to use the -P option to see what kind of key and IV that openssl is generating. I also told you openssl also uses a salt value, right. Whenever it generates use a password, it uses a salt value so that it can produce a unique key and IV. Salt will act like a nonce value, right. It acts like a nonce value. Salt is used with password for security reason. So whenever you deal with password, you must use the salt. Without salt, a password is useless. In 3DS we have 3 keyring option. I discussed about keyring option 1. Originally it uses 3 different keys, which is 168 bit, and because of parity bit we need additional bits and it will end up in 192. But internally it will throw away every 8th bit, every parity bit it will throw away, and it will only take the 168 bit, okay. That's keyring option 1. We saw a demo. Then keyring option 2, there are only 2 keys. So essentially you will only need 112 key, but because of parity bit what you will do is you will provide a 128 bit, right. Automatically the algorithm will throw away every 8th bit, every parity bit it will throw away, and it will only take the remaining 112 bits for actual encryption decryption. Later we also saw a demo of AES using the CBC mode of operation. I told you the IV is always equivalent to the size of the block size, which is 128 with AES. The key will change but IV won't change. AES support 3 different keys, right. So AES we learned that it support 128, 192 and 256, okay. So okay, we will stop here. Thanks for joining with me today. I will see you again in the next episode. Thank you.